So so basically classifications are the techniques where in which you will try to judge or basically provide a label in the form of 0 or 1, in sense where 0 could be not spam, this we see, and spam, so and so forth. So the way we formulate the problem was that we would be providing the data and then we would be having the label. This is ground truth. In this, we would be having data would be in the form of columns. We would be having future x1, x2, say n futures, and we would be having m rows. Against that, we would be providing labels that would be in the form of 1, 0, 0, 1. So this is what we have provided. Now we want to solve this problem in the future when anybody gives some new user gives us some data or some information, we would be able to tell whether his data, according to his data and the problem we are solving, this belongs to label 0 or 1. Since we are just dealing in 0 and 1, so the this is this is a binary class classification. If we have on a more than two classes, three, four, then that's a case of multi-class classification. So that we're gonna see in future. There are algorithm which is capable of giving the labels in among the multiple values. Though we can achieve that from logic regression as well, but that's a technique we're gonna see. But given this, now we formulate that okay, this something my hypothesis, the way we do in linear regression. In this case, we first formulate a equation which was x1 theta 1, x2 theta 2, likewise xn theta n. Eventually, the thing which is matter is that we want to find these thetas here in this case also. But now as we are trying to solve a problem in which we want something between the range of 0 to 1, so we saw that there exists a function which is known as sigmoid function. Sigmoid function has the capability that when which is also denoted by sigma, the capability of this sigmoid function is such that if this value being passed into a sigmoid function, the output would be in the form of between 0 to 1. How the we see the graph for something like that, zero point 0.5, the graph will go like that. So when this whole value after computation is 0, it means zero point 0.5. Above then, it's more than zero point 0.5. So we generalize that keeping a threshold of zero point 0.5, which is a general case, we say anything greater than equals to zero point 0.5, we call it class 1, and less than zero point 0.5, we call it class 0. So now this function was figured out. Now, as we try and when we do or train any algorithm, we required a cost function. So in linear regression, the cost function was very straightforward, very intuitive, that which was something y I minus y hat square 1 by n, basically mean squared error. This was in linear regression. Here, it was nothing. It was very simple. It was just negative log of your s theta x. So for we have class y equals to 1 and y equals to 0. This is minus log of 1 minus something, 1 minus of the same y hat. This we see. And so now we have the objective, we have the cost function. Only thing was required is to do the gradient descent algorithm, which is very simple for all the thetas. Keep iterating, keep updating the thetas by taking the derivative of the cost function of this thing. So this we keep doing it until the things got converged. So everything is same as linear regression. This is what we have seen. Now suppose now this is done. Now you would be training a multiple models. There could be model 1, model 2. Again, from the same applying logic regression. Now you need some kind of mechanism so that you can say that okay, model 1 is better than model 2, or model 2 is better than model 1. So we need some kind of matrices here. On behalf of that, we can evaluate our test data. This is we want, right? This is what we want. So let's go into this direction. We would be looking into the evaluation metrics. Generally these are 4 in numbers. There are many more, but these are the top ones: accuracy, recall, precision, F1 score. Now let's discuss accuracy, and most of you already know what accuracy is. That suppose we have this train data, we have this test data. we created a logic regression model, and this test data we have say 2000 rows. So we would be having 2000 labels. Why? Which is 0, 1, 0. This is already provided in the test data set. We check model 1 and y hat gives us 1, 0, 0, 1, so on and so forth. Accuracy checks, we just check that okay, this is 1, we got 1. So 1. I mean this is true. 0, 0, true. 1, 0, false. So eventually we see how many are correct. I mean out of 2000 times, how many times our predictions are correct with respect to the actual ground truth. So we see okay 1200 times they were matching. True were matching with true, false were matching with false. Basically 0 matching with 0, 1 matching with 1. So we give it the accuracy is 12,000 upon 2000. So very basic, 6 by 10. So 60% of the accuracy. So we could be having model 1 with 60% of accuracy. We could be having model 2 with 70% of accuracy. And based on accuracy, we can say model 2 is better than M1. So this is one case. Now, so I think accuracy is pretty much clear to everyone. Now, but can anyone discuss any idea or any scenario when even the accuracy of 70%, this is 60%, but M2 is better. M2 is a bad model as compared to M1. Can we have some example in this area? So basically, so question is that okay, okay, we studied accuracy, that's okay, but is accuracy it's in itself a sufficient matrix? So can we rely on accuracy always? For me, initially it looks yeah we can rely on accuracy because actually we are matching true with true, false with false. So what else we want? But but okay, this gives us model 2, 70% or 60%. But there could be some scenarios where accuracy is not itself sufficient. So if someone has any idea quickly they want to share, we discuss that.
In terms of time.
Let's not discuss about the time in terms of computation. No, some other. I mean, yeah, time is of course could be one thing that in a maybe time taking in model 1 is lesser than time computing in model 2. Then I can take the call
Yes.
60% near to 70%. Let's go with M1. So this is pretty much a good answer. But yeah, but anything more? If we are not if we are agnostic of the time taken.
Maybe the threshold we are not
So okay, so I said
true
threshold is
value is
same.
there.
Threshold is same in both the cases.
Okay.
0.5, 0.5.
So are you
Okay.
referring to the precision of the
I'm just talking about accuracy. So I just wanted to discuss some cases where this 70% is kind of a deceptive. I mean, even if my accuracy is
Yeah.
90%, but I'm not sure
Yeah.
if a model is good. So in this scenario,
So this is we are predicting, right? So maybe
yeah. Hmm.
it may happen that it may over predict something, uh, or we know that. So for example, how can we say? Um, let's say, let's say, uh, let's say we are predicting. I'm giving a random example here. Let's say we are
Yeah, yeah.
predicting where we can see the sun tomorrow or not, and a
Okay.
model based on some values input, it says 0% chances that we can see the sun tomorrow, but it may
Hmm.
never happen. It may be so according to its data, it may be interpreting that it is 0%, but we cannot rely or it may say 100%, that 100% there is chance that we cannot see the sun tomorrow, and the other model will say okay, there is 90% chance.
Hmm. Hmm.
You are
Yeah.
overestimating some of the parameter, and you are saying that that's why you are computing to 100%. So this could be one of the scenario that comes to my mind.
Okay, perfect. So understood. I mean, even if the model is 70%, which is more than 60%, but there could be the cases in the next example, this works better. So this is maybe you are trying to refer. So okay, I mean, so now I'll take you one example, and then we all would be aligning now. So suppose my test data is such that again, let's take some very very strict scenario, maybe uh, detection of cancer. Take this example. We have 2000 examples. I mean, we all know that cancer is not something which happens to everyone. It happens very rarely. So you will agree with me that the test data which we would be working, test data in practicality always comes from some real source. So real source always behaves what exists in the reality. So number of cancer patients among all kind of patients are very rare. So suppose I have this data of 2000 data points in which my output is that whether this patient has cancer, no, this patient has cancer, no, this patient has cancer, no, yes, and this is how we collected data. And suppose, for example, out of these 2000 examples, my data is such that they are just for no, just for the easy mathematics, there are 10 patients who got cancer. So 990 are non-cancerous patients, right? Now suppose I created a model, take it as a very vague or stupid model, which what it does, it just says that my all the predictions are zero. What happened? My predictions are zero. So you will see in this case also 990 upon 2000. This is gonna be the accuracy, which is, let's make 990. So you can, which is almost 100, 98% of the accuracy. But it, so I mean, now you can assume that even the accuracy looks good to me, 98%. But how it treated the cancer patient, it says all the cancer patients are not cancerous. They do not have cancer. So they just give probability y are zero. So even you see that this how deceptive the accuracy can be. Even after showing accuracy is 90%, because all the cases, 990 cases which are 000, it predicted zero, a stupid model. For one also predicted zero. So I'll just check 0 equals 0. Okay, one, true, calculate all the true, which is 1990 times we are correct. Out of 2000, 98% of the accuracy. So now I think this will make everyone understood that accuracy could be deceptive, right? Are we clear with this point?
Raj, maybe can I add one thing?
Yeah.
The models that we build are based on the input that we provide, right? So it could happen that the set of input provided to one model are themselves are not so ideal, and that's why they are predicting way higher than it should be.
Yeah,
The other
I mean,
one, yeah, other one maybe have good set of
good
input,
setup.
and that's why they are predicting less, but they may be more. Yeah, they, they,
Totally
they
agree.
may be,
So
yeah.
yeah, totally agree. So my model could be very well, but do not have data. My model could be a stupid one. But whole idea, whole point or gist of this exercise is that the accuracy is a deceptive term, right? They if they perform very bad. I mean, out of 10, they says they do not have any cancer cells. So this is what it is. That's why accuracy is not a reliable always. I mean, it's a good matrix to make a start, M1 M2, which is better accuracy. Let's calculate that. But we need to always make sure that accuracy in itself is not always sufficient. This is one of the example, right? So now, therefore, to handle the accuracies, we come up with something called as recall, precision, and F1 score. So if this part is clear, we will move to the, and you will see this whole four matrices together are called a part of confusion matrix, which we gonna understand. Okay, so let's come to recall first. So I will not go into the slides. I'll just use this blank slide. Recall. Okay. Now, guys, there are four scenarios. I mean, take it handle. Let's handle it this way. True classes. True classes means the actual nature of the data. True classes could be 0 or 1. It means when actuals was 0, when actuals were 1. When actuals was not spam, actuals was spam. So we created a box here because I want to explain something. So here we write y. Y means actuals 0, 1. Here we write y hat. Y hat has a predictions. Predictions could be 0 and 1. So we write 0 here, 1 here, right? So this 2 by 2 matrix, this 2 by 2 matrix is called as confusion matrix, because this matrix in itself capable of sorting out all the confusions. So let's how it is. What it says, let's try to understand. Maybe y is 0, y hat is 0. It says that actual value of actual level were 0. The model also predict the 0. So 0 to 0, right? This 0, 1. This says that, and here we comes up number. How many times? How many rows? How many rows? How many rows which were marked 0 to 0? Here, actuals were 0. I mean, they were not spam class, but my model predicted it is a spam, right? So these numbers are called as, this comes up into this category where actuals were 0, model marked it 1, right? Now this box says when actual were 1, maybe spam class, but model says that's not a spam. So that number comes up here. And finally, when actuals were 1, model also predicts 1. That numbers come up here. So if we again write things here, 0, 1, y hat, 0, 0. This is 0 always considered negative. So these are true negatives. True means whatever the model says, what is the actual, they are true. I mean, they did the right predictions. 0 means negative. 1, 1. In this box I am talking about, actuals 1, model predicted 1. Very good case. So they are true. 1 means positive. So these are positives. When model is 0, actual is 0, model says 1. So 0, 1, contrast, which is false, positive. It means model has detected this positive as a false. So this, all the numbers which comes up here. So this term I am definitely sure you must have heard of somewhere, that 20 case, these many were the false positives. It means models were 0, actual were 0, model said it once. So model predicted it false. And what model predicted? 1, which is positive. So false positive. Now this case, actuals were 1, I mean, and model predicted 0. So 1, 0 means false predictions. Model predicted 0 means negative. So these categories are known as false negative. So this is how we divide numbers into here. So for example, again I was working on this 20,000. I will keep the same example, or maybe take some better example, 20 100 data points. So you could, in reality, you could see in matrix in this way. 50s were in this category, 0, 1, 0, 1, 10 predicted correct, 60, 20, PCC 70, 80, 20. So this way you can see that how your number of test examples could break. So let's try to find the accuracy again from this number. Accuracies are all the cases where 0 were zeros, all the cases ones were 1. So basically this block 0, 0, 0, 0, 1, 1, this blocks. So accuracies will be 50 plus 60 upon all the sum 100. So just an example, 60% accuracy. So this way we can calculate accuracy. And now we're gonna see how we calculate recall, precision, and what is the relevance. Understanding the relevance is first. But before that, let's draw this box in bigger. And before moving ahead, any questions? 0, 1, 0, 1, true positives, true negatives, 0 becomes 1. Actuals were 0, model says no, that's a 1. So model predicted it false. What model predicted? Model predicted true, positive, 1 is positive, false positives. 1, actuals were 1, model says this is class 0, model predicted false, what it predicted? Negative, false negative. So this is how you will see this confusion matrix is there. So it could be, they write it yes over. So the sequence can be anywhere. It's just that yes, yes are true positives. Yes, no, 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 no. Here are true negatives. This is 1, this is 0, this is 1, this is 0. 1 predicted as 0, false negatives. 0 predicted as 1, false positive. So they could be anywhere. It's just the order we write it here. So that's what we have seen. You just need to focus what converted what. So any question in true positives, false negatives, and true negatives before moving ahead.
I think it's clear.
Okay, perfect. Okay, this part is clear. Then let's move ahead to the recall part. Okay, this is done. This is done. We're gonna see recall, and then we're gonna see precision. Let's start with recall.
So, Raj, one question. Yeah.
Yeah, sure.
So, for this evaluation matrix, right, or the evaluation matrices for the
Mm-hmm.
logistic regression. So, we are we are seeing the possibilities of only these four, right? So you have either 0 or 1, um, and then you have the predicted value, which could be yes, no, and then the actual value could be yes, no. So there are four possible combinations. So this does not mean the 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 quantity of variables, right? It is just the possible situations or
Possible
scenarios, correct?
situations, yeah. So yeah, possible situation on the binding class when we have this could be like example not spam classes, and every time this varies with the problem we are solving. So this is how you will see in practicality model says not spam, model says spam. Then you will say how good your models are which compared to the actuals. Then these could be the four scenarios which exist because one can convert into zero, one can convert into one, zero can convert into zero. So all that's why you have 2 by 2 matrix, right? However,
Okay.
if in future you are working on multi-class classification, for example, instead of zero, there are three classes: class one, class two, class three. Then your matrix will look like something here, right? So how many C1, C1? So so then your true positive will not be just one block. True positive would be set of two blocks. Your accuracy would be considered by taking C1 converted into C1, C2 converted into C2. So accuracy is always diagonals.
Okay. Okay. So sorry. Can you tell the last point, the C1, C2? So
So
you,
for example, here we are dealing with two classes, one and
yeah,
zero. So
yeah,
therefore, it's just a 2 by 2 matrix. However,
correct.
if we are solving a multi-class problem where label could be class 1, class 2, class 3, for example, 0, 1, 2, right? Could be,
Uh-huh.
for example, a uh, rainy day or sunny day, or maybe what else?
Yeah,
Winter, right?
winter.
So three classes could be
Okay.
there. So here in this
Okay.
case, this is actuals, this is predicted, then we would be having a 3 by 3 of confusion matrix, right? Because
Understand.
actual model says it's rainy day, but it could be sunny or it could be winter, just an example. But all in most of the cases, when we solve, I mean, when we solve Viney class, this is what it is,
Yeah, understand.
right? So let's clean it again.
But
Now you,
sorry,
yeah,
sorry,
please, yeah.
but this confusion matrix or the evaluation matrix,
Huh?
it could happen even in a non-classification problem also, right? Like a linear
How?
regression also.
How?
Uh,
In linear regression, we have continuous data. For example, my actual value, 10,000 rupees salary, 12,000, 11,500, 14,000. Here my salary is, my model predicted 9,000, 0.5, 8,000, 0.10. Then is it, it's not possible to make a confusion matrix for over these all the numbers, right? Confusion matrix are always between the classes. Here, these are the classes: class 0, class 1, class 0, class 1. Did you get my point? So it's
okay.
hmm,
Yeah,
on continuous you can just make a kind of kind of lines, something continuous lines, right? You can make histograms that you can check, compare histograms, so on and so forth. But here it is. Here, I mean, in linear regression, it's pretty much very clear. I mean, I'm dealing about salaries, which is continuous data, or prices. I just need to focus on the mean squared errors. I mean, which is a very good metrics. How closer we are with the actuals. So that's in itself is a sufficient matrix. But here, as first example, as I shown, accuracy is sufficient. But then we saw accuracy could be a deceptive one. Therefore comes the factor recall, precision, F1 score all together. Because now we're gonna see why they are different matrices. So let's focus on that, right? So I'll start with the recall scenario, recall and intuition of that. Okay, now consider a case where we have created a we have created a computer vision problem. Computer vision, we have a camera we take photo of some traffic light and we say this is a red light. This is a non-red light. Or take another example. Okay, take this example. This is from KD tricks analysis. Our model is supposed to tell whether the new ongoing customer or the new customer is gonna default. This gonna be positive class, means 1, or non-defaulter, a 0 class, right? Now you have given this work, you have to create an algorithm, you have to decide the matrices, you have to decide some threshold. Okay, I'm okay with the 0.5 threshold, I'm okay with 0.6 threshold, maybe 0.4. Now you as a developer, or you will ask with business objective, what is more important? I mean there is a risk. Whatever the threshold, you increase the threshold or you decrease the threshold, some classes gonna reverse. Zeros for example, if I increase the threshold 0.6 or 0.7, what does it mean? It says that if the value is greater than 0.7, I'm gonna call it defaulter. If this is less than 0.7, these are non-defaulters. So what exactly happening in practical, which in background? There could be the cases where from 0.25 there were defaulters, but my model condition is so strict that even it says some of the defaulters are non-defaulters because of this high threshold. Here they wanted to focus more on the cases where if they predict this guy is a defaulter and the actual has to be defaulter. So there are two scenarios to whom you want to penalty. You are okay if defaulter is predicted as non-defaulter, or you are okay if non-defaulter is predicted as defaulter. There could be only two scenarios. By keeping a threshold, there could be the scenarios where some of the defaulters, I'm okay if my model says this guy is a defaulter, which is defaulter, model says that is a non-defaulter, basically class 1, model says class 0. Or there could be the case where model says actual is non-defaulter, model says 1. So being a business customer of a bank, you not customer, the person who are developing this algorithm, you have to take a trade-off between these two. I'm okay with these cases if my model is, for some of the scenarios, my model is making defaulter as non-defaulter, or the scenarios where model is saying this guy is a non-defaulter, model says okay. For example, I'm a new bank. I has to be very strict. I'm some new bank emerges and it has to be very strict. So this bank needs to be make sure all the defaulters should be captured. All the defaulters should be captured. In this scenario, there could be trade-off that they make some innocent as a defaulter. So for them, this is the case, right? So as a new bank, I would be very strict to all the defaulters because limited money, everything is limited. We cannot accept more defaulters. So I have to predict defaulter. While doing so, it's okay if my model says some non-defaulters as defaulters. This is one case, 0 converted into 1. Now there could be another case which lies in this thing. This says that I do not want to lose my customers in this year. Just try to understand. This is some existing bank. They want to increase their presence into some cities. Now they are okay losing some money, but they do not want to say any non-defaulters. Do not want to do any non-defaulters as defaulter. While doing so, they are okay that I say this defaulter is non-defaulter, or they want to keep all the one happy. So this is the second scenario. With the help of recall and precision, we handle both the scenarios, right? So is this point clear, or I'm happy to repeat it again? The scenario 1, I'll write it parallel. Scenario 1, scenario 2, new bank, limited money, old bank want to increase their presence, right? So you will agree, the new bank guy, they are very strict. They want to make sure that their defaulters are captured. While doing so, it's okay if they make some of the non-defaulters, this is a true case, they make some of the non-defaulters defaulted. It's okay. They are okay to lose some innocent guys. They will not give loan to them because the model says one, but they are okay with that. But they want to capture these people very strictly. These are new bank. Old bank scenario. I'm okay. I'm okay in this scenario. I want to bring more customers into the bank. So I'm okay in this scenario when this person was defaulter. My model says that this will not default because I want to keep all the innocent people non-defaulter is non-defaulter. This we want to cap. This we want to hold. While doing so, we may do this thing. We may say we may give loan to the defaulters, right? But because model says 0, so we are okay with this scenario. This scenario is totally reverse, right? So here, this we want to hold on this thing. While doing so, we are okay with this scenario, making non-defaulter or predicting non-defaulter as defaulter or not giving loan to them. No loan. New bank okay with that. That's how we see. Here case, give loan, even though they are defaulter, but this could happen because we want to take hold of this case. We do not want to say, we do not want to make any non-defaulter as defaulter, no, right? These are the true cases. Now let's try to understand scenario 1 with the help of our confusion matrix. Is the analogy clear in both the scenarios?
Yes, it's clear. Yeah.
Perfect. Actuals predicted 0, 1, 0, 1, true positive, uh, true positive, true negative, false positive, true positive, false negative. New bank scenario. I want to reduce no loan. I want to keep hold of these people. Let's start with this new old bank scenario because this is easier. It's okay if I give loan to these people 1 to 0 because I want to hold these people, right? So let's try to understand this term. True positive class 1 converted into 1 divided by true positive plus false negative. Just be with me. True positive plus false negative inka sum. What exactly they are? They are actuals. I mean, if we do the sum of true positive and false negative, this is equals to number of ones. So which is nothing but actual trues. So I can write it true positive of an actual true. Right now, if false negatives, take this term. If my model is saying this number actual is 1, my model is saying 0. If this number is lesser, this whole number will become lesser and we will increase the recall. Recall will increase. Recall will increase. So what does it imply? What is the intuition behind that? It says that this model focuses more on reducing the number where V model says this is a defaulter, but this is a defaulter, but we will not, but actual model predicted as 0. So defaulter being predicted as non-defaulter, we want to reduce these numbers. So basically we want to reduce the false negative. So when you want to reduce the false negative, in this case, this is a formula. By formula, if we reduce this number, this whole term will increase. Or lesser the denominator, higher the whole value. So recall will increase. So while comparing your two model M1 M2, if my focus is more on reducing the false negative, I do not want my actuals, my defaulters to be predicted as non-defaulters. I do not want that. So in this case, I want a higher recall. So right. So this confusion matrix always helps us do that. So we have to align our business objective. We have to convert that into very layman term what they want. If business objective says that use the matrix such that your false negative should be lesser, it means your model should not say or should not ignore any defaulter as non-defaulter. My defaulter, therefore I want to reduce the false negative. Why? Because I want to reduce this term denominator. So while doing so, the recall would be increased. Therefore, if we have two models M1 M2, the recall is say 80, the recall of it is 70. So I would say model M1 is capable of keeping false negative lesser as compared to model 2. So in this scenario, I will focus on the recall along with accuracy. So for example, if after result M1, M2, accuracy is say 70, 75, recall is 82, uh, recall is say 78, 78, 84, or maybe 84. So in this scenario, if my focus is to reduce the false negative, I might, since accuracy is same, but I would put more emphasis on recall. So recall becomes my evaluation matrix because 84 is greater than 78. This model is capable of reducing the false negatives. Now there could be the trade-off. False positive would have been increased, but that's okay. Whole objective as per the business. So this always confusion matrix always aligns with what business need. So this we modify with respect to business need. Business says do not ignore all such kind of people. Where actuals, this is actual, but you are saying this will not default. For example, I mean, see how even in the scenario, cancer scenario, how mischievous it could be that that person comes for his diagnosis prognosis. Basically, he got cancer, but my very first visit in the hospital says that this guy is okay. I mean, you are okay. So this guy might wait for month or 2 month, 3 months. He might move from stage 1 to stage 2. So you see how uh, I mean, this could be wrong for with this person. So here our emphasis is that recall has to be lesser. Recall has to be lesser. Recall has to be high. False negative has to be lesser. This is a very good example. So what could be the decide while doing so? This could be the case is that you make this guy which who do not have non-cancer. You say it you have got cancer. So on the very first visit, he could be afraid, but eventually they will not go for the some kind of treatment, or they will go for the second opinion. In the second opinion, he might be corrected. So this scenario is still okay. This is not that much bad as compared to this scenario where the guy who got cancer marked as non-cancer. So this may cause him from stage 1 to stage 2 shift, because I mean this is pretty much reassurance. If I get something, I'm reassured that you are okay, then from my back of my mind I would reluctant to go for the next second visit. That's the human mindset. So that this could cost him. So being a hospital, if I'm building some solution to the hospital, I in this scenario specifically, I want a higher recall, which means I want to reduce this scenario. Uh, 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 True classes marked as given as zero classes, right? So I think this is how the relevance of recall after accuracy. Is this part clear?
Raj, whoever named this confusion matrix, he was really right.
Who,
This is not this is not
so,
clear.
sorry, which part?
Whoever named it
Confusion matrix.
confusion
Okay.
matrix, yeah, he was
Yeah,
clever
it's
guy.
really
Yeah.
confused.
So
So
what
so
I
No, just
understand
understood.
one.
is no,
Please,
just
please.
a minute,
Yeah.
sorry. So what we are doing here is we are basically in the recall, we are just trying to see the percentage of positive predictions done by the model, right? Because true positive is correct, correctly uh, correctly predicted by the model, and the denominator, which is true positive plus false negative, is actual positives, total number of actual positives, right?
Right.
So here we are just trying to see how accurate the model is predicting again, right? So I don't, that's where I'm getting confused.
So
Here
yeah,
is, yeah,
here, see, the actuals is a combination of false negative plus true positives, right? This row.
yeah, yeah,
So I have written this way,
yeah.
right? So so I want to focus you on onto this part. You just tell me what does false negative means. Uh,
False
so that.
negative means it
Mhm.
is incorrectly predicted by model to be negative. That means it was actually positive, but model said it is negative.
Right, perfect. So actually it was positive. Model
Negative.
says negative. So let's be with me with this with the cancer, because that's a pretty much recall is used highly over there. So this means that actual were the person has cancer, right?
Yeah,
And no, negative means this person has
no cancer.
no cancer, right? So for example, suppose, so this case, what actual were person got cancer, but you tell him that this person has no cancer, right? So
Yeah,
what could be the implication? The, the
he
implication
could
could be
die.
that he
He
could
could
die
die.
perfectly, because he would be assured that I am okay. Just so we will not go for the second opinion, right?
Yeah.
Meanwhile, what could happen? He could have moved from stage 1 to stage 2, whatever, stage 3, right?
Mhm.
And after 1 or 2 months, when his health starts deteriorating, he might go for the another visit after 3-4 months, and then he got to know that you got cancer, right? So this is a wrong prediction. This is a false negative. So false negative costs such patients a lot. Now this part is okay, right?
Yeah, yeah,
Now
yeah.
now you as a developer, new startup, you are building this tool for a hospital.
Mhm.
So what do you want? You want to these cases to be very lesser, right?
Yes. So
So
we want
I
this
want
recall to be 100% basically. The true
basically,
positive.
yeah,
Yeah.
100%, but that will not never happen. But
Mhm.
eventually the right wording is we want lesser false negative, right?
Right. Right.
That now put this lesser term here. We want lesser false negative, right? So this
Mhm.
means we want a higher recall.
Higher recall. Yeah.
Now
Okay.
okay, now you are one startup, second startup is also there. This is a hospital customer. A startup one created the model, their recall come 85%. A startup two recall come 80%. Hospital will choose this guy, right?
Mhm.
Because this startup is capable of reducing the false negative.
Awesome. Yeah.
He
Yeah.
made his model so well that his recall is 5% more than startup 2. Their models
Okay.
are better, right?
Yeah.
So therefore recalls comes handy in such kind of handling, where we want lesser false negative, right?
Yeah.
So now I think this part is clear, right?
Yes. Yes.
Perfect.
One more question maybe.
Hmm.
Uh, why are we only focusing on false negative? There may be some scenarios where we
Yes,
actually don't want false positive. We may be
we
good
will
with
come to
false
that. We will
negative.
come to that.
Okay.
So
Okay.
so
Fine.
that's why you will see. So because there's never ever the case that recall is the only. We see accuracy, because
Mm-hmm.
we see recall, we
Yeah.
gonna see precision, and we gonna see best of both, which is
Yeah. Yeah.
F1.
Okay.
So the question which you have asked, that lies in precision.
Okay.
So okay. So false. This is clear. This is clear. No,
Raj,
recall is clear, right? Uh, so
hello.
yeah.
I joined little bit late, so I will just ask regarding this accuracy. So with this metric, accuracy will be like true negative plus true positive divided by all these
Total.
four, correct?
Total. Hmm.
Okay, okay.
Yeah. Okay, so maybe see the recording now in which I mentioned that why accuracy is not a could not be a always a reliable metric, right?
Yeah.
So okay, so this part is clear. Let's try to build now another use cases. Uh, in y 01, y hat 01, true negative. This is false positive. 0 converted into 1. 1 converted into 0. This is false negative. And 1 converted into 1, which is true positive. Now, we wanted the scenario which we wanted is that we want to penalize the cases where false positives, the classes 0 are converted into 1. One scenario I'm gonna give you here. This is false positive cases. In recall, we see the use case where reducing the false negative is important for me. Now we want to see the scenarios where I want to put a check on false positive. I do not want this case or lesser cases where the person is innocent or non-defaulter. The same scenario which we see in the bank, we say that this guy is a defaulter. So basically new bank, but I'll give you one better analogy with that. Classes zeros converted into a 1. We are building a red light mechanism. Traffic light in itself is also a classification problem. You got an image of a light. Here would be 3 colors. The center we are targeting, which is red color. My car is approaching. The camera based solution see the image, did this prediction. This is a red light. So what could be the cases if we created a solution here? If there is no red light, this example, my model says that's a red light. So that's the cases which we do not want. Always, if there is such higher false positive, this means that my car will, the practical implication, whenever this approached, my car will put a brake before reaching the traffic light, might hamper the cars which are coming from the back. Another scenario, this is a pedestrian crossing signal. 0 means pedestrian is not crossing. Model says pedestrian is crossing. So every time that's the car stoppage, which is an unwanted result. So just an example. So here in such scenarios, you want to put a check on the false positive too. Or if we want to keep the example very simple, so bank is the one thing. Non-defaulter guy converted being said as a defaulter. I do not want old bank case. I do not want to do that. So here, this term is known as precision. This says that I want my model to be precise. Technically, we're gonna see which is nothing but true positives upon true positives plus false positive. Again, true positives upon, let's see, true positives upon false positive, which is predicted y. Predicted y equals to 1. So see how beautiful it is. Recall were true positive upon actual y equals to 1. This class. True positive is true positive upon predicted y equals to 1. Fp plus Tp ka sum. This number is here. So theoretically, layman language definition, it says that I want my model to be precise, that if there exist 10 y equals to 1, how well my model is able to solve that. Now this I'll take you back to the problem which we solved. We got 2000 examples. 990s were 0. 10 examples were class 1. The same cancer patient class 1. Let's put it here. True positive. So this part we want to here. Precision will focus on such example where you are also focusing on the false positive. So we have to be precise. So in precision, we want FP cases to be reduced. So we want to reduce the FP. It means we want a higher precision overall. So precision, a higher precision means this model is capable of having lesser false positive. The scenarios where person with class 0 being classified as 1. So this is false positive. This is a false positive. We want to reduce these numbers. Therefore, we want to increase the precision. So this boils down to that precision takes care of a control on false positive. So true positive upon true positive plus false positive. This is known as precision. Recall. control on false negative. True positive upon true positive plus false negative. Let me just confirm one thing. Yeah. Yeah. So this is recall. Now this answers your question when you said that there could be false positive. So when you create a model, when you solve any business problem, you are at the point of creating a matrix, optimal matrix. You always ask the customer which trade-off you want. So this is a trade-off between precision and recall. So this is a universal case. When you want a higher precision, your recall will decrease. Or when you want a higher recall, your precision will decrease. So here we ask customer that whom you want to whom you want to be important. I want false negative to be controlled. One, zeros converted into zeros. I want to reduce such numbers. I will focus more on recall. I want zeros converted into one, false positive. I want a higher precision. In general, whenever we create a solution, we always do a trade-off of both. In general scenarios where I am not very much particular about recall or particular about precision, I will take a trade-off. I will choose a number for which precision and recall would be calculated. And now you will agree, this all boils down to the threshold you choose, right? Actually, your threshold 0.5, 0.6, this decides that you are converting a class into 1 or 0, right? So thresholds, optimal threshold will decide the precision values. And finally, you got a precision recall. Now somebody asks that I do not want to deal with precision recall together. I want one matrix. I just want one matrix which takes care of the both false positive and false negative. So that matrix is known as F1 score. So F1 score is nothing but the harmonic mean of precision recall, which is F1 is given by 2 precision into recall upon precision plus recall. So this matrix takes care of a trade-off between precision and recall. So if I am solving a problem which is general, I mean, I am not that much particular about recall. I do not want particular precision. I wanted my model to have a decent precision and decent recall. So no specific problem, business objective we are solving, I can go with F1. And in the scenarios where we are very much particular about false negative, we are going for the recall. Very particular about false positive, we can go precision. In general, when we solve problem, we compare recall precisions and we take the best of both the birds, which can also be given by F1 score. Right, one increases, other decreases. So the harmonic mean helps you do that, helps you take a trade-off between both. So eventually they will give you a one number. Being a model, I will choose the one having the F1 score. So thing is that we want all the models for which precision compared with precision is better, we will choose the higher one. Higher the better for all the cases. Higher accuracy, the better. Higher precision, the better. Higher recall, the better. Higher F1, the better. Now, it's just comparison between among models. Among model, how to choose one. So therefore, these four matrices are there, which is capable of getting calculated from the confusion matrix. Now, so yeah, this is one thing here. Any doubt in recall precision? Just focus here. Recall is pretty much very clear when I want to reduce the false negative classes. So I will choose, yeah.
Well, Raj, I understood the precision and recall, but you mentioned the F1 score, right?
Okay.
Can you give an example
Eh,
where exactly you would require?
Okay, sure. So recall and precision. I want a scenario where if we try to control false negative, we would be having more false positive. When we try to control false positive, we would be having false negative. Now I want to build some solution where I do not want to penalize one particular type of class. I do not want to penalize the people who were defaulters and being converted, who are defaulters and being given a non-defaulter. I also do not want to penalize someone who were actual good, I mean the class negative were given as 1. So I want to keep a trade-off between that. So in this scenario, I will go with F1 score, because this says that do not just take a higher recall, neither the precision nor the recall, just take the best of both. So in this case, we go with recall and precision together as F1 score. So the use cases which lie in this scenario are the ones which are not specific, which are in general, a general scenario.
Oh, okay.
General scenarios come up here, right? So this is something for a spam converted into not spam. This is not something which is very much affecting a human being or someone. So I'm okay to have a decent recall and precision. Before that, I can go with F1 score. But with a scenario which lies from the domain of very strictness, like banks, hospital discoveries, they are pretty much very much in terms of recall and precision. So whenever if you get the chance of reading any hospital paper, so there are surveys where they have done some researches on thousand samples, they will always and always would be talking about the recall and precision. They were strictly mentioning that we got 20%, 80% recall, we got this much precision. So you will always will hear these two terms. You will seldom hear the term read the term F1 score there, because these guys when do some research, some experiment which are of high importance, they are very much particular about handling false negative, false positive. So right, so if we want to handle these classes separately, go with recall precision. But I'm okay, my scenario is not that important, so I can go with F1 score, right? These are
So,
the cases.
sorry, another question. So, means these evaluation matrices, the examples what you mentioned are like an instantaneous thing or a particular at one point of time. But from the algorithm point of view or from machine learning point of view, will the algorithm over a period of time learn by itself and then try to balance the recall and precision matrices
No,
automatically, or
no, no. So algorithm just works on training data, but after training, how good you are doing, you do on the test data. Matrices we apply on test data, so this has nothing to relate with the algorithm. But
algorithm itself?
but yeah, but this indirectly it helps. Indirectly it will come into the play. How? Because you cannot just do recall and precision by yourself. You have to play around with the right threshold, right? Because threshold
Yes.
are the one which is capable of converting 1 into 0 or 0 into 1, right? So threshold is something which is meant to be learned from these experiments. So you will learn the thresholds.
So,
Also,
so it means that on the test data, we play around and then we play with these matrices, accuracy, precision, etc. And then the pressure threshold value is then again kept back on the algorithm. For,
yeah, you get
or
the
it will
threshold
help.
appropriate. Yeah, it will help you get the best threshold. Now, since you have asked this question, let's break the hierarchy of train test split into. So far I just told you that we split into train and test, right? Now there's a third category also, we sometimes use, we sometimes do not use. This is known as train, well, or known as validation in short, well, and test. So for example, here it was 70-30%. Here we break into say 60, maybe 20, maybe 20. So the matrices number which you are getting with the recall, you can play with the validation. This will help you. You will train model on the 60. You will validate your thresholds over the validation, and this test finally is the unseen data. So basically this, so what happened in general, for example, you are training your model for 1 lakh of iterations. So basically 1 lakh of iterations we are training the model. We train model for say 1000. We put a rule when number of iteration, basically training is going, we are training the model, but in the block we also add a block here. We are doing a training, we train, there's a one Python block which is nothing but if number of iterations divided by 1000. This means every 1000 we want to do something. If this is equals to validate on validate data on validation, right? So this says this way you also keep improving your model after every 1000 iterations over the validation data. So here you can see, okay, alpha threshold 0.6 give me the best number. Okay, for after this iteration 0.5 is working, 0.4. So validation gives you a nudge, I mean gives you upper hand to evaluate work, changes your different alpha theta threshold values over the validation. Once everything is done, your training is done, you have done the decent validation, you can test on the test data. So this is another kind of split. We generally do not do that because we are okay training the models on the trained data and finally checking on the test. But both the scenarios boils down to that. With the test data, you can find, you can select the threshold and check which one is giving what precision recall. So eventually you're gonna see one direct mechanism of doing that. So we're gonna see that. So just leave it here. Let's come to this graph. So what happened? I created a graph which is FPR and it has everything related to the precision recall. And this graph becomes very easier once you understand. This is FPR. Let's try to understand. FPR, let's try to understand this system. It is false positive upon false positive plus true negative. False positive upon false positive plus true negative. So basically predicted by equals to 1 this class upon false positive plus true negative, actual 0. Eventually, what do we want with this term? With this term, I want that these cases should be reduced. I mean, if these are false positives, I want to reduce this number. I want to reduce this number. So overall, I want to reduce my false positive rate. Simple, go with the name, false positive rate. We want a lesser false positive rate, right? So in this graph, this is a graph 0 to 1. This is a false positive rate. We want this false positive rate to be on a lower side. We want this number, whatever the number is here, we want on this side. This you will agree with me. This is true positive rate, which is given by true negative upon false positive plus true negative, which is actual zeros, y equals to 0, just opposite of this. I want true positive rate to be higher side, this side. So basically we want some points here. So here, these graphs are nothing but different threshold. So if I take threshold equals to 0.1, I can have multiple threshold. My threshold could be 0.1, then 0.2, 0.3, 0.4, 0.5 till max. I can take max threshold as 1, which is not possible. I mean, this is possible, but will not make sense. So what we do, at this threshold, we choose the threshold 0.1, we calculated these two numbers and we plot the numbers which comes out here. Then we choose threshold equals to 0.2, put them and then calculated the false positive, drive these two numbers and put it here. And this way we derived all the point, right? Now you keep on doing same thing here. You tried all the models. These are different models. Model 1, model 2, model 3, model 4. First thing first, best model out of these all would be the one which lies on the upper half. So out of these, just looking at the model, best one is this one, right? Now best alpha, which best alpha we will choose? We will choose the best. Each alpha will give you two rates. If we are here, this will give me true positive rate. And this will give me a lesser false positive rate. Less false positive means higher precision. The name itself suffices. False positive rate, if it is lesser, my model is highly precise. True positive rate, better recall. So we want all the points which lies in the upper hat. So these points, these all alpha. So let's, if this is one graph, this graph look like this. From threshold as 0.1, we got two value, this value and this value. For next threshold, we got this value. Next threshold, we got this value. Basically, you will create a ROC graph. Then based on that, you would be having, right, threshold, 0.1, 0.2, 0.3, so on, and all these value of FPR, value of TNR. Now this ROC will tell you, okay, being a business business objective, I will see, okay, this alpha is fine. I am okay with 70% of this number. I am okay with 60% of precision. This alpha, sorry, this threshold will give, I can choose. I can even go further ahead. So this is something if I'm okay with this precision FPR or this number, I can choose this alpha. So basically what we are doing, we are creating a graph by changing the theta thresholds every time from 0.1 to 0.2 and then just plotting onto this chart. So we want a higher precision means we want to go in this direction, higher recall means we want to in this direction. A best combination would be the cases which lie somewhat here in this area, because this area are the one which corresponds to high precision and high recall. You can take a trade-off. Okay, I mean, by this threshold, this is a precision, this is a recall. I mean, one will increase, one will decrease. So you can take a call, right? So this graph you can plot also for the precision is up. Now everything is up to you. There's no kind of fixed logic. I can plot a graph between precision and recall. I take I take threshold equals to 0.1, then 0.2. I'll plot all the points. It will go somewhat like here. Then I can choose. Okay, okay. I mean, these are different alphas. If I take this alpha, suppose I take 0.2, precision is lesser, recall is 20%. For example, recall is 40%. Let's go here. Okay, this is 50%. This is 62%, for example. Okay, this alpha, which is 0.4, for example, this is 75. This is 80. So maybe as an experiment, I can see, okay, 0.4 is okay to me. Initially, in the model one, I'm okay with 75% of the precision and 80% of the recall. So that's a trade-off. So whenever you want to do a trade-off between precision and recall, for that, of course, you need to choose one threshold. Best, and this is a graph which you can write a script and plot it simultaneously. So this you can visualize like that, nothing else. So this is just kind of visualization, and this is known as receiver operating characteristics. This term came from the study of entropy being done during the time of World War something, World War II, when so so that's the history. I mean, you can read when receiver operating characteristic were this term were defined. So this was defined when during the war with German, uh, the Allied were used to send the information to their secret spies. They want to decode. They used to decode in terms of information bit, and therefore this term were derived at that point of time. So there's history, but even I do not remember. I forgot. But yeah, so this is receiver operating characteristics. For us, it's nothing but a graph of choosing a threshold and plotting it. That is it. I mean, it's up to you. You want to do that, you do not want to do that. Only thing is that we want a upper side here. We want a reduced false positive rate and a high true positive rate. That is it. So I think this part is clear. And I mean, this pretty much just name is able to suffice. False positive rate has to be lesser. Therefore, you want to move this side. And you also want to have a true positive rate. You want to move this side. For and just to keep the best of both birds, you need to choose the alphas, right? So I can choose maybe this alpha, this alpha. Best alpha would best threshold would be the one which lies in this direction. This is the target. So in general, when we do multiple experiments, we change parameters, we change learning rate, etc. I mean, we do a lot of examples. So we take many examples. So this is also a one way of plotting all the models, evaluate on test data with varying thresholds, and we choose the values, right? So I think we are almost with the time. So any doubt in that?
What is
So
this
I
formula here for true positive rate?
so do not go with that. Maybe after 15 minutes, I'll tell you the relation of exact relation of FPR and the precision. This is related with the precision. So if you subtract, for example, uh, just
Because
a moment.
here you mentioned that true positive rate. That's why.
Yeah. So just a moment. So let's see that. I want to show you one thing. It'll take some time to negative, false, positive, positive, false, negative. Just try to understand, and then I'll tell you about the derivation of this. False positive plus true negative. If this all boils down to false positive upon actual zeros. So it says that out of actual zeros, how many zeros converted into one? This you are targeting a precision. You want to control precision. I mean we were zeros, but some of us get converted into false positive class. We want this number specifically is known as false positive rate. So for example, and let's do one thing. Base facility. This is written here. False positive plus two negative. Take explicitly here. This whole term here. This becomes 1 minus false positive on false positive plus 2 negative. So this becomes false positive plus 2 negative minus false positive upon false positive plus 2 negative. This is a new term. I do not want to go detail in that. This becomes 2 negative upon false positive plus 2 negative. So this becomes opposite of actual truths, actual zeros converted into zeros out of all zeros. So just mathematics. So I don't want you to understand this specificity. No, this is what we derived here. See, I just focus on to the term FPR is false positive rate, which is very well understood with the formula. False positive on the numerator, and this is actual zeros. Actual zeros. This just says that out of actual zeros, how many converted into one? We want to put a check on that. So we want a false positive rate lesser. This means we want to target all the thresholds which lies in this areas. This boils down to towards the recall. We want a higher true positive rate. So we want to target that number, that thresholds for which the value lies in this area. So out of the best would come up which lies somewhat here. So all the thresholds, these thresholds will give you two numbers, one number this, one number this. Based on these thresholds, I can choose which one I want to keep. This is just a visualization of keeping all the thresholds and choosing these two numbers based on that. So let's come after 15 minutes and we will see this graph again. But what this is totally what I've seen earlier. This is nothing but how to choose the best of precision and recall. This is everything is same.
Okay.
So
Okay,
yeah.
maybe
So
we'll discuss after that.
yeah. So maybe let's take a 10-15 minutes. We get refreshed and then it's 8:48. So guys, I'll take a 15-minute break and then we meet at 9:05. Is that fine? 15-minute break. I'll quickly come right. Yeah. See you then. Yeah. Let's keep it like that. Yeah.
Hello, Giri? Hello?
Everyone, so I'm here in case you want to start, we can, or else wait for 9:10. Or meanwhile, any question? Have that.
Uh,
So let's share my screen once again.
Hello, Raj.
Yeah. Hi.
Maybe question not from this lecture, but last lecture. So can we go to the cost function? Or you want to continue this one and maybe at the last I can have a questions.
I think
It
that
is
would be
okay.
better, else the
Okay,
context will
okay.
change. But
Okay,
we,
okay.
we
Good,
can
good.
have that.
Yes, we will continue with the current context and maybe at the end I will ask.
Definitely.
Sorry.
Sure. Since I have written 9:10, so just give me a heads up. If uh, I'll wait for 9:10, then we start. Meanwhile, let me do. In reality, also, if you are solving classification, you create confusion matrix a lot. I mean, again, in we generally use this. We wanna see in future. We generally use scikit-learn library. This is a library, very well written in Python. It contains all the models inbuilt, all the matrices, whether you want to use linear regression, logical regression, random forest, all the matrices. Low.
If you are sharing screen,
Uh,
please
it's not visible.
not you're not sharing. I
Oh,
think.
sorry. Yeah, thanks. It's visible.
Yes.
Yeah, thank you for. Okay, so I was saying, in general, we use, there are many models. There are many there are confusion matrices. We use confusion matrix a lot for logic regression or basically any kind of classification problem, agnostic of the algorithm. So there's a there the library which we're gonna use is known as scikit-learn. So this library is very well written. I mean, it contains all the models which you want to create, all the matrices. For example, if you want to create a confusion matrix, they are inbuilt function. Now, some function, some object dot confusion matrix, you pass y pred and y true. They will give you all the four numbers by itself. Accuracy, recall, precision, you can use that. F1, you want to calculate F1 score, you can calculate. So all the functions are written. You do not need to write any function by yourself. Everything is there. All the functions has a clear documentation that it expects y pred values are y true. Thing is that everything would be very easier. So it's just one line code and it gives you all confusion matrix. So let's discuss the graph of ROC. Okay, so this is confusion matrix again, one for the last time. True negative, false positive, false negative, and now 1 1 2 positive. So recall were discussed, precision were discussed, then accuracy was discussed, and average score was discussed. Now we saw this graph. Let's try to capture the intuition. This is false positive rate. This is true positive rate. You can also think it as recall. This is recall as it is recall on y-axis, right? Your threshold is a knob. Consider it as a knob. You change its value. You change threshold 0.5 to 0.6. The values of recall and precision will change, right? You change it, you decrease it or increase it, the recalcitrant value will change. So ideally, we can say that uh, over the 2000 test rows, where we have y predicted depends on threshold being 0.5, 0.6. We can create a table where we mention, okay, 0.5, when threshold is 0.5, recall was 80, precision was 60. When this was 0.4, this was some 75, this was 65, for example, like likewise. So basically with this we can create a table, and if we plot it being precision here, being recall here, so this every threshold, you choose threshold, every threshold will give you some number here, and you plot it. This graph, this is just a graph, this is known as PR graph. So very easy, because precision and recall ka graph, P and recall
So
curve, PR curve.
for every threshold value, there will be different graph.
For every threshold value, there will be different value of recall and precision.
Sorry,
So
can you repeat?
for every threshold, there will be different value of recall and precision.
Okay.
So for example, I choose this is recall, this is precision. So suppose मैंने threshold लिया 0.4, right? So it gives me recall as 60 or precision as 70, some random number, right? So you will choose on this axis 70, recall 60, you will mark this point, right?
Okay.
Then what you will do, you will change this threshold 0.45, right? So maybe this gives you some number 0.45 threshold, it gives you some number here. You can, so this way you can plot all the points against all the values of threshold from 0 to 1, right? This one function is there. So then you join this graph. This graph is known as precision recall ka graph, PR curve. This is PR curve. Now this will give you an optimal, this is just kind of visualization, a tool, a dashboarding tool, which can give you a clear picture. You do not need to look into table. You can just have a look. Okay, for my scenario, if I am okay with any recall greater than this, any precision greater than this could be achieved by this. So this becomes your optimal threshold for your future application, right? This is PR graph, but this graph is little different from that. Here it is recall, considered recall. So ROC curve. So the curve which we discussed is precision recall earlier. This is slightly different. FPR recall. FPR is false positive rate. Just try to look onto the function, the formula precision. Precision formulas was this one. In layman term, how many times we predicted y hat as 1 among actual ones. This is actual ones among predicted one. So how precise we are. FPR is almost same. It is prediction 1 upon actual zeros. It says that out of all the zeros, how many we converted into 1. So this is false positive rate. And what we want a false positive rate to be lesser. We want a reduced false positive rate. Because zero is converted into 1 in the evaluation. This we want to reduce. So we want a false positive rate. So same thing, same alphas, same thresholds we chose. We calculate FPR, direct formula is there. We put it here, and when we plot this graph. And then we take a proper threshold. Okay, for example, this model, I'm okay with this FPR and this precision, this recall. So in general, everything formulate is that you focus on recall, you focus on precision, and also you say, so how the problem generalized, I want FPR to be less than 10%. Based on that, you make yourself into this bracket, less than 10% is the false positive rate. Then I'll choose the higher recall. So you could choose this recall, you could choose this recall, because everything is under this 10%. You could choose this recall. While keeping these recalls, I also see in PR ka graph mein what was the precision. Basically, this is a constraint. You can choose the best of recall and precision. This is how the people generally interacts with the graph. They look onto the graph and choose the best. So these numbers comes from the customer, or basically the client. They says that devise a solution such that you should restrict your false positive rate by 10%. So ROC curve will itself curtail down your threshold into this region. Now I want more than 80% of recall. So this, if my 80% is this, so now this whole solution boils down to this square. So these points are available. These are the thresholds are available. You can choose the threshold out of that for which the precision is higher. So this could be done by a simple mathematics function, etc. It's just the kind of visualization. You need some visualization here. So for example, this is model 1, this is model 2. Just by having the look, I can straight away avoid this model 1. I do not want that. My model 2, all the points are way better than model 1. Model 1 dash version 1. This is totally below this green line. You can straight away discard this model. So this visualization helps instead of doing all the calculations by function, creating an Excel sheet, then checking. No, plotting a ROC graph helps you do that. That's the only advantage of ROC graph. You can just visualize which model is working fine. So so eventually everything boils down to that. We have precision, we have recall. These in itself, accuracy and F1 score, these in itself are sufficient to choose the best matrices as per the need. Also, and when someone demands, I also want to take care of the false positive rate, I will deal with the ROC curve. Else, I got a PR curve, precision recall curve. However, creating a ROC curve is very easier. You will see in the ROC curve, you can check and you can choose the best thresholds. It's all about choosing the best threshold. That's we want. So best threshold always comes with the experiment on the test data. You try with different thresholds, 0.45, 0.46, 0.48, 0.52, and then you will see, okay, out of which threshold I get the best set of these numbers, and then I use that in my future. So therefore this ends our evaluation matrix. So anytime in the exams we can, in the exams, so the things could be like that. We could ask that there could be, you can see the questions, for example, given the scenarios, why should we go with the precision, why should we go with the recall, or which one you will go ahead. So basically the questions could be in the form of the business objective, and being a business developer, which metrics you gonna work upon. Maybe we give you some confusion metrics, and we should be able to calculate the precision recall out of that. For that, I have drawn this a number of times, that you should be able to understand this thing, that 0 to 0 is true negative. So if you know that, then it's where you, I think, learn every aspect of matrix evaluation for classification problems, right? So you can just practice. Internet, there are many numbers. You can practice a scenario where they give you a number, you could be able to understand. So next homework, if time permits to us in the free time, it makes sense to understand when to they will answer the what I have just taught here, when to focus more on precision than recall. And maybe you can have these questions from ChatGPT, when to focus more on recall as compared to precision, and then you would be able to relate what what we have seen today. But yeah, this completes our all the evaluation metrics, and this is what last I'm gonna discuss here. So let me see the time. So, so it makes sense. You guys have maybe by next class just try to read about precision, recall, and F1 score. I mean this is sufficient, and then I can take the question in the next class. Okay, so let's bind up our today's session with Akaike information criteria. Sometime what happened? So there are two aspects: train and test. I mean, we already seen matrices based on test data that okay, these matrices we can see which model is performing better. But there comes one more matrix, or very important matrix, which is known as AIC, Akaike information criteria. It measures the relative quality of the model. It is nothing, but we will not come up with how to comes it. Ln is log with natural log. So log of L was the likelihood function which we see. If you remember, the likelihood function looks something like this: log yi log of yi log of h theta plus 1 minus yi log of 1 minus h theta. Hypothesis. This is a likelihood. If you remember the previous class, we told that we want to increase the likelihood, because while doing so we would be able to find the best set of thetas. So we calculate the natural log of lk minus plus 2k. This is number of variables. This is a penalty factor. Since we want to increase the maximum log likelihood, negative is there, it means we want a lesser value of AIC. So M1 model, M2 model, you calculate AIC. It's very simple formula. It suppose comes out whatever it comes out. Whoever lesser is a better model. So this thing is, this evaluation matrix is from the point of training, and F1 precision, recall in from the point of test. This way you can use Akaike information criteria to tell based on the training which model is better. So yeah, again direct formula is there. So basically what it says that I am model M1, I am model M2. After the training, I give you some set of thetas. I also give you some set of thetas. So if I give you this set of thetas, your maximum value of log likelihood should be higher. So therefore M1 should be better than M2, because I am giving you a best set of thetas. This is what AIC does. So since we want to increase the log likelihood, therefore negative sign is there. We want to decrease the AIC. Lesser the AIC, higher the maximum log likelihood. Higher the likelihood means better chances of thetas. That is what it is. So this it's okay. This is optional, but good to have. I mean, this is the whole premise of logistic regression. We want to maximize the value likelihood. AIC is just negative of that. That is it. Plus 2k is the penalty. Number of variables. More the variable, that should the AIC should take control of that, because we do not want unnecessary addition of unnecessary addition of a model. This is this number is added here, but eventually it's nothing but the negative likelihood. That is it. So you can I just mentioned just to make it fulfill completely the session, but this is optional. If time permits, please do read about the Akaike information criteria. In general, we used to compare models. We used to compare two models. Lesser the value of AIC, lesser AIC, I choose that model. Better it is. Right? So with that, I mean, this is what this is what it is. So in general, the business objective was discussed: hypothesis formation, cost function. After cost function, we decided the gradient descent, and then we see matrices. This is the important part, which I think is clear: accuracy, recall, precision, F1 score. If then even if we want to be more precise, we plot the ROC curve. That's okay. And before during the training, during the gradient descent training, best model is the one which has the lesser AIC values. This is a summary of logic regression. Yeah. So please just read it whenever you get the time, or maybe some questions from ChatGPT just to compare, just to understand yourself with the precision recall. And then yeah, any question we can take in next class. So I think guys, this is what logic regression is, and this thing always gonna same for all the stuff. I mean all the things which you have read. Any problem you're gonna solve in terms of classification, you would be dealing with this matrices for sure. So you would be seeing random forest, decision trees. This is also classification, regression, both helps in both. But if you want to evaluate any classification model, this is what it is. Yeah. So now I think we got 4 minutes. We can take the question. Yeah. So guys, over to you. Hope we were able to at least understand precision recall, and the examples which I discussed with you in terms of hospital, distinctness in hospital, and the bank finance domain.
Raj, one question. In the last slide, basically we said that depending upon the curve, we will decide the theta value, right? Or the threshold value. The threshold value. This is the same threshold value which decide whether the logic is 0 and 1, or is it different?
Yeah, no, same threshold. Yeah.
Okay. Yeah.
So reason being, maybe what could happen. This y class was 0, for example. 4.6, it was predicted right. Y had predicted right. What could be the cases that when I make this threshold 0.7, this y hat becomes 1. So basically,
Right.
this threshold we increased one false positive, right? So
Yeah,
when we
yeah.
do that, our precision will vary. So yeah, you are right. So somebody asks the question, maybe about this maximum log likelihood, basically the derivation of cost function. So maybe this class we do not have time, but I can take this in one of the free session, that how this cost function is derived. This is what we want to do. So guys try to understand one example. If you're able to, that's okay. You remember when we take this example, probability of head at t. So suppose you some likelihood of, what is the likelihood of HST? The likelihood of HST is simple, 2 by 3. 2 head out of these 3. This is a if I say my maximum log likelihood is 2 by 3. So suppose I do not know the probability of H. Initially, I mean in general we know the probability of head is half. This is because I know. But being this experiment being done, we saw HST as an event, and this is nothing but the raw data which you received. You have received the raw data. Now you do not know whether the raw data is biased or not biased. So consider probability of head as theta. So this becomes probability of head theta dot theta. Probability of tail becomes 1 minus theta. This becomes my log likelihood of, so this, let's theta 2 or theta square 1 minus theta square as theta 3. To find the best theta, we differentiate. Let's differentiate it. I'm trying to do something here. So differentiation of theta square is 2 theta. Differentiation of theta is 3 theta square equals to 0. Taking theta common equals to 0. This theta cannot be 0. So second equation becomes 2 minus 3 theta equals to 0. This boils down to theta equals to 2 by 3, which comes out to the information is coming from 2H 2 by 3. So what I try to understand you here is that the same log likelihood thing we do in the example when we try to understand how the cost function is derived. So this is the same experiment when we do here, when we choose this thing, It's just that we did it. This was theta. We did it on a generic level over rows. So maybe next time we're gonna discuss the cost function again if required, and we're gonna see how maximizing the log likelihood helps you get the best theta. Right? But examples was the same thing which I mentioned. Here I know that this thing can be observed when I see occurrence of H is 2 out of 3. If I calculate the log likelihood of that, would be theta dot 1 minus theta. Theta is the probability of H. The probability of that would be 1 minus theta. And this is, we do not know this is biased or unbiased, so we cannot say it is half. So when we calculate the derivative of this, the way we do, we come out to be theta 2 by 3. This is something which is intuitive, but we're gonna see that in future. But having said that, we do not need to worry about, because this is the cost function of logistic regression. Cost function of linear regression was the mean squared error, and why it was it, and this was very intuitive. I mean, we can understand this thing. We can understand because these are continuous values. I can see, okay, 10,000, 10,500. Okay, 500 ka difference ka square. We understand. We want to reduce this number. This is also the same thing. It's just that here we are dealing with the probabilities. So cost function are not some mean squared error, rather derived from the log likelihood, which is minus log of S theta x. So this is again, so maybe in some time we will discuss that. Not maybe before our exam, but maybe after that. So if no question, I would be sharing the paper with Dr. Snail ma'am by this week. 7th is your exam for syllabus, and again there would be MCQs. MCQs would be having questions from the area of linear regression, logistic regression. You should be able to classify that which problem is supervised, which problem is unsupervised, what is the classification problem, regression problem. You should be able to understand about the categorical variables, continuous variables, and you should know how to calculate the squared mean errors at least, etc. And and questions from gradient descent. So basically the area of scope for this paper is linear regression, logistic regression fully, but we would be focusing more on the fundamentals. So basically matrices, which we see today, and gradient descent. So yeah.
Anything from Python will you ask?
Python, see Python, I will not ask, because not every one of us are okay with Python, and it even doesn't make sense to ask from the Python, because object is just to understand the machine learning fundamentals. So let's keep up to that level.
So all questions will be MCQ based, right, sir?
No, subjective would be there. So maybe I can give you a business objective, and I can ask you that which whom and whether you will go with the precision or recall. So you should be able to justify that why you are going with the precision recall. And having said that, there is no fixed answer. Somebody will say precision is okay, somebody will say recall is okay. We will take, both are correct. It's just the reason which you are giving. If the ideology of yours. So you should be able to calculate the precision. If I give you some confusion matrix, you should be able to calculate the recall. So therefore, this thing you should know that what are false positive. So that is it. So I write it.
So we can do our own assumptions, and based on that we can solve
Of course, for subjective,
problems.
Subjective, you can have your assumptions, and this is how in practical we works, because there's nothing fixed in there's nothing fixed. It's your assumptions. It has to be in the right line, right direction, but everything is fine as far as you are able to justify logistic regression, matrices, gradient descent. Please focus on this algorithm. Focus how this algorithm works. Yeah, that is it. Next class is gonna be k nearest neighbors. This is a very good algorithm, but this will not come into the exam. So 7th, yeah.
On 9th also we won't have our classes, right? Because we have exam on that day.
How?
Yeah, the exams are on 7, 8, 9.
7, 8, 9. So 9 if would be free, then we can have classes, because I think it's very tight. We need to close by 6th. We need to close by 6th of April, because 12th is the last semester day. This is what Snail ma'am told to me. So we are left with basically 1, 2, 3, 4, 5 classes, max 6. 3 classes I want to keep for generative AI, where we would be actually using the agentic AI tool. So maybe I can take 1 session on RAG and 2 sessions on agentic AI. Even this is what, because this makes sense to take in this scenario. Therefore, for machine learning, I am just left with 2 to 3 classes, and I need to cover k nearest neighbor, decision trees, and random forest, 3 algorithms. 4
Okay,
algorithms
okay, sir.
basically.
Okay, sir.
So yeah. So let's have class on 9th.
Okay, sir.
Okay. Okay, then see you on 7th. 7th is the exam, right?
7,
So
8,
Girdhar,
9.
I think I'm not sure, but Girdhar is here. Okay, so
No, unfortunately, he's not.
no sure. So I think 7th I have to be there for the exam.
Oh, okay. So you will be invigilating.
That I need to ask ma'am, because last time it was all online. But
Okay.
so I'll ask Snail ma'am if I need to come.
Yeah, sure. If you can come, then it will be good. I mean, we'll get to meet you as well in person. Yeah.
Yeah, sure, definitely. I would like to. Okay, then. Thanks, everyone. See you. It's already
Yeah.
being
Thank
late.
you.
Yeah.
Thank you, sir.
Thank you,
Bye-bye.
Raj.
Thanks. Bye.
Bye.
Thank you.